We'd like to welcome Yang-Shui Wang to the University of Minnesota. And Yang-Shui will be giving our data science seminar today, as well as being here all week for people who would like to meet with Yang-Shui. I've also set up some two tutorial kind of sessions that if you're interested, please send me email. So Yang-Shui's even though he's a young man, has already a very distinguished career in multi-field materials, and especially recently in machine learning methods for interatomic potentials. Yang-Shui, please.
Thank you very much. So good afternoon, everyone, and thank you for Mitch's great introduction and invitation. And it's a very nice campus here. AI for science is a very super hot topic nowadays, and I'm very happy to be here to share with all of you that our latest advancements in the machine learning interatomic potentials. So today my talk will be not involve too much technical details here, but focus more on the motivations and the machine learning data-driven applications in material science. So if you have any questions, please feel free to stop me. So today my talk will be divided into these several parts. So first I will give the background and motivation and instruction of machine learning potentials. And then I will introduce a delicate model, which is called atomic cluster expansion method, mainly developed by my postdoc supervisor, Professor Chris Ochner. And then I will give one application of this base model in the numerical analysis aspect, which is the generalization error analysis in the machine learning interatomic potentials. And then I will introduce an intricate model, which is the message passing ACE, also known as the MACE model. And given the exceptional performance and very good generalization capabilities of MACE model, and I will give you one introduction in this direction. That is our team's recent work of the pre-trained foundation model, MACE MP0. And then finally, I will give the summary and my based on my personal understanding, the future direction of the AI in material science. Okay. So first of all, the background and the motivation. So you may have already seen these figures before, that the models can be categorized into different kind of scales based on the accuracy and capabilities. And so which scale model should be chosen, the electronic structure model or the classical interatomic potential? This requires a balance between, there's a trade-off between the accuracy and computational cost. And achieving the optimal balance between the accuracy and computational cost has been a challenge in the field of molecular modeling and simulation for a long time. And the Golden Bell Prize, which is known as the Nobel Prize in the high performance computing, has been awarded twice in recent years to teams contributing to this direction. So reflecting the widespread application this field receives. And over the past 3 decades, a series of concurrent multi-scale methods based on the domain decomposition has been developed to achieve this goal, aiming to combine the micro-scale model accuracy and the macro-scale model efficiency. And the common multi-scale coupling method, including first the QMN coupling model, which is widely used in the biology and chemistry field, and also the atomicity to continuum coupling, and Mitch is the expert in this field, which is widely used in the engineering and material science. And these two methods was the main focus of my doctoral research. And our experience shows that the difficulty in the multi-scale coupling model lies in its construction and also the implementation. Because due to the lack of consistency between different kinds of models, that obtaining mathematically rigorous and consistent coupling model is a major challenge. And developing consistent multi-scale coupling model that are simple to implement and widely used remains the main bottleneck in the development of multi-scale coupling model. So over the past decade, with the rise and widespread application of machine learning and artificial intelligence, there's a different path to bridging the accuracy of the electron structure model and the efficiency of classical empirical potential. And this path is known as the machine learning interim potentials. And the goal of machine learning interim potential is to achieve the efficiency of classical models and the accuracy of ab initio or the electron structure models. And currently, at least, the machine learning interim potential can be achieved is that the accuracy can be systematically improved at the cost of increasing computational complexity. So these two figures verify this claim that, so here is the benchmark test of the mechanical property of silicon system. And here the GAP model obviously is not the closing company. It's one of the commonly used machine learning potential here. And the z-axis here is the relative error compared to DFT. And this figure shows that compared to the classical empirical potential and the GAP model, the machine learning potential can reach the near DFT accuracy at just a moderate sacrifice of computational efficiency. And this figure, the ACE model that I will introduce today, is a very delicate model, a smaller model that can reach near GAP accuracy, but with like a 40 times faster of computational cost. Yes. GAP is a famous machine learning potential based on the Gaussian regression. Yes. And the construction of machine learning potential mainly involves 3 steps. So the first step is to generate a good data set. That this data set should cover as much of the computation space as possible. And at the same time, we want this data set to be as small as possible because the data set is typically generated using the quantum scale model, such as DFT. And the second step is to construct the descriptor that quantitatively capture the local atom environment, known as features or descriptors. And this descriptors provides mapping from the atomic positions or coordinates to the real number or to the quantities or to the features that to capture the essential characteristic of the atom local environments and to accurately capture the physical systems. And this descriptor should follow a basic physical symmetry such as translation, commutation, and rotation in wires. And in the third step, the appropriate training or learning method is chosen based on the second step, the descriptor. And this may involve techniques, for example, the linear least rail or Gaussian regression or the neural network methods. And the development of machine learning potential has seen rapid progress in recent years, and with new methods emerging almost every month. And depending on the different descriptors and the regression methods, this table and figures lists all common descriptors and their corresponding machine learning potentials. And the first method I introduced today is the atomic cluster expansion ACE model, while the other method is based on the ACE model, the message passing neural network potential MACE model. And I will provide the details later on. And machine learning potential have had profound impact in different fields. For example, to construct the phase diagram of water, or to predict the stable structures of metal alloys, something like this. However, compared to the empirical force field, compared to the classical potential, for example, the Lennard-Jones potential here, that the machine learning potential still face challenge. So the first challenge is that they show poor transferability, which means that a potential you train on one given system cannot predict in another system, in another different system. And secondly, due to there still have a large number of parameters in this potential, and the computational efficiency of machine learning potential still lags far behind compared to the classical potential. So to address this challenge, the machine learning potential should develop in parallel from 2 directions. The first is to improve the computational efficiency, that the model should become smaller and more accurate. We call it a delicate model. So for example, the atomic cluster expansion is that model. And to improve its transferability, and the model should become large and more robust. And this, for example, is the message passing neural network ACE potential. And it's worth noting that the robustness refers to, because the robustness can have different meanings in different contexts. So in our context, the robustness means that the MD, the molecular dynamic simulation, will not goes to the non-physical configuration, because the current generation of machine learning potentials will sometimes lead the system to the non-physical configuration. So this is the main problem here. And so the robustness is very important in developing the machine learning potentials here. And the above is the introduction and background of the machine learning potential. And now let's begin with the introduction of the atomic cluster expansion, a delicate model here. And maybe you have noticed that this is not able here. This is just to remind me that I need to change an ACE potential now on my laptop. And during my introduction of this section, you will see how easily to get the ACE potential. Okay. Okay. So today I will only give a brief introduction of ACE and only point out the yes.
Just before you go on, I want to make absolutely sure that I understand the problem that you're dealing with.
Yes.
Okay. So you're saying just some general interatomic potential machine learning. Could you say again what the problems are and how these things are going to solve them?
Okay. Okay. So there are two problems for the machine learning interatomic potentials. So the first one is low transferability compared to the empirical one. That the low transferability means that you train, for example, the carbon system, a potential, it is hard to simulate, for example, the silicon system, something like that. So this is the transferability. And the slow computation, which means the efficiency. For example, here, here, as you can see, the empirical potential, the computational efficiency is something like that. However, the smallest model or the prettiest model that we have now is something like that. So there's still a gap, right, between the empirical potential and the machine learning potential. Because, for example, the parameters in the empirical potential, maybe you have only like tens or hundreds of parameters in it. But this one or this one has like hundreds, thousands, or even millions, something like that. Millions of parameters.
So ACE and the other and MACE,
Yep.
These are special families of machine learning interatomic potentials which generalize well and train easily.
Yes, yes, yes. Thank you for the summary. Okay, so I will only point out the key properties of ACE model, and for further information details, and tomorrow I will give a lecture on the details of construction and theory. Okay, so what is the ACE model? We say that ACE is a physical-inspired, polynomial-based approach describing the symmetry of particles. And symmetry means rotation, translation, and permutation. And the key thing in ACE model is that the A is the ACE basis. And ACE basis is a polynomial that maps the atomic configuration into the real number, so that the total energy of the system can be represented as the linear combination of the coefficient C, which need to be determined by the data, and also the ACE basis B. So the ACE basis B should satisfy the same symmetry of the original system. For example, the invariant on the rotation, and the invariant on the translation, and also the invariant on the permutation. Okay, so this is the first key property of ACE model. And then we say that ACE describes the many-body interaction of particle efficiency. So first of all, ACE, or actually the general machine learning potential, always make this assumption that the total energy E can be decomposed to the site energy, which means you decompose the total energy into the local contribution of this site energy, something like this. And this is very important because it's really reduced the dimensionality, because you can, for example, the A spaces here, you don't need to map the total configuration into the real number energy, but only the local atom environment to the energy. It's very important. And then ACE incorporates the high body or many body interactions, something like here, that for example, the Lennard-Jones potential is very famous, the pair interaction potential, and the Stinger-Weber potential is the famous three-body potential simulating the carbon or silicon systems. And ACE can theoretically involve infinite many-body interactions. So it could be theoretically very accurate. Yeah. So this is the second properties.
So sorry. So it's right here. You do the cutoff around one single.
Yes. Yes.
But for the classic like Lennard-Jones, they basically consider global.
Well, there's still the cutoff of these empirical potentials. Yeah. But this assumption actually avoid the long range interaction here. And the long range interaction should add it empirically.
So maybe you're gonna cover this, but so EI of R, I mean, that's the real many body energy.
Yeah.
And what you're doing is what you have really is an approximation of that.
Mhm.
And as the number of basis elements increases.
Yeah.
You have a convergence result.
Yes. Yes.
Are you gonna describe that result?
I will describe this tomorrow.
Okay, but that's just to clarify.
Yeah.
There's actually, you need as you add more and more basis elements,
Yes.
you're adding more and more atoms from the environment.
Yes.
And you have a systematic approach, is what the ACE is, a
Yes.
systematic approach
Yes.
to have a rigorously convergent expansion.
Yes. Yes.
Just double check. So when you say many body interaction here, you really mean many body ionic interaction, right? Because for the same system, you can just have more electron and the energy could be different.
I think here we are, the machine learning potential is basically the administrative modeling, the simulation.
It's a many body in an atomistic sense, no really electrons.
Yes, there's no electrons here. Yeah. And the third property of ACE is that ACE basis forms a linearly complete set of the symmetric polynomials. So which means that the ACE model is actually a linear combination of the coefficient to be determined and ACE space B here. And once you have the data, and the data set is contains the atomic configuration R with its DFT energy and forces, and maybe other observations like variables obtained by DFT calculation. Once you have this data, and then because of this linearity, you can solve the coefficient C here by simply using the linear regression method to minimize this quadratic loss function. So here is the energy loss, and here is the forces loss. And also you can add other observations like real stress, something like that. And also typically you need to add the radializer terms to avoid the overfitting, something like that. And I will give the detailed construction theory tomorrow. And the accuracy of the ACE model has been validated in numerous simple systems. For example, we can use ACE to actually train the cross-grain potential, and also the ongoing work with speech group that we can train ACE for twisted bilayer graphing, and also the generalization error for dislocation, and also the accurate force prediction by ACE, and also this like gamma energy prediction, and also the grain boundary simulations for metal alloys. You can also use ACE to simulate this simple system. So the primary purpose of these figures is to demonstrate the good prediction and generalization capabilities of the ACE model for this simple system. And in conclusion, So ACE is a physical inspired machine learning or data driven model. And it is a polynomial based approach used to describe the particle symmetry and many-body interaction of the system. And ACE basis is complete. And ACE is friendly to mathematicians because it is essentially a polynomial based approach. So it can have the approximation theory rigorously and also the generalization error analysis and also the uncertainty quantification and also the inverse problem, something like that. And if you can see the code or the practice or the implementation of ACE model to train an ACE model, you only need, there are actually only 3 hyperparameters to control. For example, the first, the body order, how many orders you need to truncate, for example, 2 body or 3 body or 4 body. And the second one is polynomial degree. That is the maximum degree of the polynomial you want to approximate, and also the cutoff radius. So actually you can train an ACE model in 10 minutes. So let's see what happened here. Yeah, it's done. So here is that training ACE for like 3 minutes, less than 3 minutes. And here is the training error, IMC and MAE. The energy is quite low, like 0.5 MeV, and force error is like 0.05 EV per epsilon. Actually, this is quite nice. And also, meanwhile, I run ACE-MD simulation. I use this trained ACE model to run AMD, that is the carbon diffusion in BCC iron, 300K. Maybe I can show you the figure, and also there's a figure here that the ACE potential, the trained ACE potential, you can see the temperature is stable, and I have, yeah, it comes out that I use this trained ACE model to run the molecular dynamics. It's at least it's stable for now. Okay. So this means that we really, the ACE model is very easy to train, just to use our laptop. And in 10 minutes, you can train ACE model. And compared to the second model I introduced, the MACE model, which is based on the message passing neural network. And you can see from the implementation, there are at least 10 hyperparameters need to tuning, to do the tuning. So, however, actually, we say that the ACE model is really a dedicated model, but however, there are some limitations of ACE model. So for example, it cannot predict the complex system. For system like usually more than 3 chemical species, and the prediction will become uncontrollable. And the second question is that if you want an accurate prediction, and the only thing you need to do, you can do, is to increase the body order and also increase the polynomial degree. But if you only increase the polynomial degree, this will make the problem highly ill-posed. So which means that the ACE model provides a linear representation of potential energy surface. However, the nonlinearity becomes very crucial when handling complex systems. So this is one of the main motivation for developing the second model I introduced, the MACE model.
So can I go ahead? Okay, so on your howevers, are those things that you've discovered just purely by computation, or are there things you actually understand theoretically?
I think this can be justified. I think first we observe it numerically, but I think these observations can be justified seriously, because it's based on polynomial approximation, and when the polynomial degrees becomes higher, then the prediction will not be accurate.
Like, what about the 3 species limitation? Is that just?
Oh, this one.
That just an observation, or is that a theoretical reason?
This one is that actually, because I haven't mentioned today is that the A spaces, the number of A spaces. If our system is larger than 3 chemical species, then the A spaces, the number of A spaces will increase dramatically. So for example, if we have 1 chemical species, then the the number of A spaces grows like linearly. And if we have two species and it grows quadratically and then cubically, so something like that.
When you say body order, what do you mean by body order?
The body order means how many body orders you want to capture this system. For example, the pair interaction.
I see, yeah,
Yeah, the pair interaction, three body interaction for.
I got it.
When you talk about three chemical species, you mean three types of items?
Yes, three types of atoms.
So you can study like pure carbon rather than silicon dioxide or.
Yes, yes, yeah.
So when you say, okay, so you have an error and how well you're fitting your data.
Mhm.
But then when you say UQ, that's addressing some other configuration that you haven't trained on.
Yes, yes.
And
Exactly.
there are ways to understand that, yeah.
Yeah, sure. It's very, actually, this one is very important because if you don't have the UQ, you don't have the error bar, then you can only say that, okay, this prediction is accurate, but how about other regions, right?
Yeah.
And how about this prediction, whether this prediction is robust? Yeah, something like that.
So when you say, yeah.
I just want to clarify what's the polynomial you're returning to?
What's the top?
What's the polynomial?
Polynomial? Okay, so because the A spaces here, they are polynomials. They are constructed by the radial basis times the Seyfried harmonic basis. So basically they are just the polynomials. Yeah. Okay. Well, I think I don't have too much time introducing this section because it's somehow to study the generalization analysis of this kind of method, but I would try to skip this. Okay, then maybe let's discuss because I have mentioned that the limitations of ACE model. So next I will introduce an intricate model, which is called the massive passing ACE model. And here's the motivation that ACE provides only a linear representation of potential energy surface. However, the nonlinearity becomes crucial when handling complex system. So here we introduce the massive passing potential here that actually the massive passing potential are a class of machine learning potential designed to learn functions of graph structured data. And molecular modeling can naturally be represented as the graph embedded in three-dimensional system because the graph's atom, the graph's nodes is actually correspond to atoms and the graph's edge represents the atoms interaction. So therefore, the massive passing networks or graph neural networks offer a highly intuitive approach to describe the atomic interactions. So the conventional construction of massive passing neural networks involves 4 steps. So the first step is to define the states and at each node, which means at each atom I, we define the states at each atom I in layer T, we define the states, which is defined on each atom as a collection of 3 quantities. So first one is the atomic positions, and the second one is the chemical species, and the third one is the learnable features or descriptors. And the second step is to construct the message. And the message M is created for each node by pouring over its neighbors with many-body expansion. So which means the message means the local atom environment information is the message. And we use the ACE model to describe this message. And then the message will be transformed into new features, which means that in the next layer, the message is updated something like this, and U is also learnable. And the last step is after T message construction and update layers, and we have a readout function to map the node state to the site energy E, and then we can describe the total energy of this system. So here is actually an illustration that, so here in the first layer, that the information will will transmit from this atom to its center atom. And in the next layer, the message passing in the next layer, and this center atom receives the information from the center atom from the neighbors of its neighbors. And this will expand the model's perception range. And so this is the basic framework for maze model, and the detail will be introduced on Thursday. So the evaluation of maze model has already been tested over many complex systems, and in each case, for example, the organic force field benchmark test, the accurate energy barrier for catalysis, and the vibration spectrum of ethanol, and thermodynamic properties of liquid water. So all these systems, the ACE model can handle complex system. Only maze model can handle this complex system. So which means the maze model show great complexity and robustness. And in summary, for the simple model, we use the ACE model to improve the computational efficiency. However, for the complex model, we turn to the maze model to improve the representational capabilities. While our discussions is mainly focused on the model methodologies, but it's important to acknowledge additional challenge in training the machine learning potentials. For example, constructing the high quality training data sets and tuning the hyperparameters in the message passing neural networks often require a lot of human effort and relies heavily on the empirical experience. Furthermore, ensuring the transferability of models across different systems requires extensive replication and validation in various contexts. And this challenge remains central to train a machine learning potential and are driving the development of pre-trained foundation model that we introduced in the following. Yes.
So you showed that infrared spectroscopy of ethanol spectrum. So yeah, this case, yeah.
Yeah.
What kind of database is required to train this model?
That's a very good question, but commonly used the data set is that you take this channel and you run MD for different temperatures, and you sample those configuration as your training data.
Okay.
Yes.
Sorry. But MD with what potential?
With DFT. Yes. Ab initio MD.
So suppose that for the molecule, you have a stereochemistry, for example, chirality. Is that possible to distinguish them with different FTIR spectrum?
This one I'm not sure, but I think the generalization capability is good.
Okay, okay.
So essentially, it should be true. Yeah.
What is the most complicated molecule that can be?
I will show you in the next that we actually the foundation model, the pre-trained model actually gives you all things, everything actually.
Okay.
Yeah. So this is the foundation model for existing materials chemistry, and we call it Maze MP0. And in summary, this is a pre-trained foundation model that can describe solid, liquid, and gas systems of materials and molecules across the periodic table. Yeah. So before introducing the model methodology, let's address two questions. So first, why do we need the pre-trained or foundation model? So first, as I said, the machine learning potentials usually custom trained for particular materials requiring significant computational and human efforts for the generation of DFT training data. And also you need to spend a lot of time to do the model training and validation. And next motivation is that the foundation model can really lower the barriers to entry in machine learning fields because the user often do not need to acquire specialized skills to use this model. And next, the foundation model can provide a very good initial guess for a specific system. When you have this foundation model, this can give you a very good initial guess. And the only thing you need to do is to do fine tuning of this foundation model. So, and secondly, what existing pre-trained foundation model or generic or universal force field we have. So the first one is specialized for organic molecules. The second one is about 56 and 73 elements. And the third one is also not all elements here, only 45 elements. And then this one were created primarily for the purpose of material discovery, only predicting the stability of hypostatic inorganic crystal. So there's no a single machine learning potential can describe solid, liquid, and gas system of materials and molecules across the periodic table. And this is our main motivation. Yes.
So what kind of stability you mentioned here? Chemical stability or physical stability?
I think it's physical stability.
You mean
It's
phase transition,
yes, phase transition, the
crystallization, or
the stable of phase, the stability of phase.
Okay.
Yeah. Yes.
So the idea with the foundation model, you like, check and see if it's already good enough for your application. If it's not, then you tweak it by further training it on.
You mean the method of train this foundation model or the use the.
I don't know, if you want to apply that foundation model
Yes.
to a different system and it wasn't quite good enough, you mentioned you could like tweak it in some manner. Is that just like further training or?
Fine tuning. You just need to pitch several data to retrain this foundation model. Fine tuning.
So what, you say there's no single MLIP?
Yes.
So the way, okay, so when I look at ACE,
Mhm.
it seems like a very systematic, can solve anything
Yes,
method, right? It doesn't,
but it cannot deal with the complex system. For example, the system contains like for example, this system. I will show you that. Here, the full battery system. There are a lot of chemical species here, and ACE can definitely not simulate these systems.
okay, so, because, okay, all the different species you're saying,
Yes, all different species
but for 2 or 3 species,
and ACE.
it's provably convergent
Yes.
and
yes.
everything is fine.
Yes, yes.
And you have
Exactly.
you can use the same polynomials, just different parameters.
Sorry.
You have the same expansion with different, and then now you still, you have to discover or compute the parameters from your optimization.
Yes.
But it is the same. It's not like people used to do where they have a different empirical potential for all these different elements and stuff. It's uniform.
Yes, it's uniform. Yeah.
I see.
So this is the background and motivation of this foundation model. And this is the training details of this foundation model that we purely use the maze architecture to train this foundation model. And we use 1.5 million computations from the materials projects. And DFT we used is a PBE without long-range dispersion, and the long-range dispersion should be added empirically by this DFT D3 afterwards. And the parameters in this foundation model is about 9 million, actually not that much compared to others pre-trained model. And the final energy can reach like 20 MeV per atom, and the force arrow can be like this. This is quite nice, quite accurate. And the performance is something like it can do several nanoseconds MD per day for 1000 atoms. So it's not too bad for this foundation model. And we also tested a lot of application of this foundation model, including the protein folding and stability, and this aqueous interface. We studied this solution behavior of salt in water, and also even this the electric interface, and also the bacterial system. At least the MD is quite stable. And however, the performance of this pre-trained model is not that optimal for every test. So we can illustrate this with an example where the accuracy is not sufficient enough, that we tested the model's performance in simulating defects in several BCC structure, including the lattice constant, UV curves, cubic elastic constants, and different formation energies, and generalized stacking fault. And we found that the prediction for lattice constant and the UV curve were good, and the relaxation of point defect structure was reasonable in terms of quality. However, in terms of accuracy, the energy error for stacking faults and also the formation energies were approximately between the relative error is like 20% to 40%, and the errors for elastic constants, the error are quite high. So overall, while this pre-trained model, foundation model can generally predict well qualitatively, but there's still a very large room for improvements in accuracy.
These are all sort of zero temperature kind of.
Yeah, zero temperature. Yeah. And furthermore, we apply this foundation model to study the grid of BCC metal dislocation. And by calculating the Pure barrier, we observed that compared to the reference model, the DFT or the QMMM method, that this foundation model provides qualitatively correct results, but lacks accuracy, because as you can see, this is quite lower, the energy barrier. And actually, we attribute this to insufficient prediction accuracy for stress in the current model, leading to inaccuracy in the prediction of elastic constants, and then in the calculation of dislocation, slip, or bleed. And this actually aligns well with our expectation for the pre-trained model, foundation model, while it has been validated across different applications and demonstrate good generalization capabilities. But we must acknowledge that and beware of that it still has some unresolved issues. And this is why we just name it the zero version. So now let's briefly discuss this issue further. For limitations, first, there's the issue of training data quality. And the quality of materials project data seems to be not a mystery. And the PBE method used in DFT isn't optimal either. So it cannot directly capture the dispersion and requires separate empirical correction of the long-range interactions. And secondly, due to the limitations in the model themselves, this foundation model currently cannot accurately describe the long-range interaction or consider the factor like magnetisms and the spin. So, and additionally, although the robustness of this model has been validated, the model needs improvements in accuracy. For example, the stress prediction and also the intermolecular interaction, which is also one kind of long-range interaction. And also the high pressure simulations, we found that it cannot behave so well in the simulations. So to address these limitations, there are two main avenues we'll be pursuing in the future. So the first, there will be some efforts to improve the quality of training data by using better data set to retrain this model, enhancing its predicted capabilities and reducing the need for system-specific corrections. And this, I think this will be announced by the next version, will be coming soon. And along this line, efforts will be made to integrate the long-range electron-static interaction and consider spin in this model. And the second approach involves using the pre-trained foundation model as a good initial guess for downstream fine-tuning, adding the appropriate data set to do the fine-tuning and to meet the specific requirements of the system. So the last part of my talk today is the summary and outlook. So today, due to time constraint, I only briefly introduce three types of machine learning potentials. So a dedicated model, which is called ACE, and an intricate model, which is called MACE, and the pre-trained foundation model, MACE MP0. And these three models are interconnected, each with its own strengths and weakness, and complementing each other in the field of machine learning potential. And in summary, I believe that this field will be very active for many years to come, and systematic applications to an increasingly wider class of systems and applications will move the field forward. And machine learning potentials are poised to become an indispensable part in the arsenal of methods available to the materials modeling community. And for the last several minutes, I will briefly outline the future direction of AI in material science based on my personal understanding. They can be categorized into 4 directions: towards accuracy, towards robustness, towards scales, and towards hot. So the first one is towards accuracy. So the first direction is, as I said, the machine learning potential has a big problem that it cannot simulate the long-range interaction. So the first one is to incorporate the long-range interaction and intermolecular interaction in the machine learning potentials. And here I listed several good references for this direction. And then next direction in this accuracy field, that is to use machine learning techniques to train or to fit the quantum levels quantities. For example, the Hamiltonian, the wave function, or even crazily that the exchange correlation function use pure machine learning technology. And next one is towards robustness. And the first one is the UQ of machine learning potential, which this part I plan to do this part in my future study. And the next direction is to use advanced machine learning techniques, for example, the multi-model learning with graph, and also the diffusion model, which is very hot last year. And this year it seems to become to MEMBA, which is a advanced transformer method. And the next one is towards scales. So there are 3 directions I want to pursue. So first one is to combine the multi-scale coupling with the machine learning potentials. And next one is to give a machine learning cross-grain force field. And next one is to use the machine learning potentials with some accelerated molecular dynamics algorithm, for example, the parallel algorithm, and also the enhanced sampling method to combine the machine learning in-type potentials with this accelerated molecular dynamics algorithm. And lastly, towards hot. So for example, the large language model in material science, and the next the application, actually this one is actually a recent article published in Nature 2 months ago. Explored potential and challenges of the strong combination of 2 hot topics in the current scientific world, the machine learning and the quantum computing. And the recent article made some very interesting attempts to discuss the impact of training noise in machine learning potential and energy on the applications in quantum computing. And what happened when machine learning meets quantum computing, perhaps only time will tell. So this is all my thoughts today. So thank you very much for your attention.
Thank you for an amazing talk. That's really great. A lot of things finally become clear to me. We'll learn more in the next few days. I open it up to further questions. Anybody?
Yeah, maybe just 2 more. So one question is, for the benchmarking, when you compare say the ACE model with the electronic structure models from BFT.
Yeah.
So what's the quantity you're trying to comparing, like total energy or something?
I mean the benchmark test.
Right. When you say example is close to DFT.
Yeah, okay.
Yeah,
This one.
yeah.
This one is the mechanical properties like the elastic constants, the Bloch modulus, and this is the I think this is the gamma surface energy, and also the formation energy for different types of defects. So there are properties, not only the total energy or force.
Okay, and which color is from the, like, how to see the figure again? Like,
You can see the arrow bar here, right? And the z-axis here is the relative arrow compared to DFT, and it's near 0 actually.
I see. Yeah, thanks. Yeah, another question is about, so you mentioned like the next model, which is only one model which can deal with a couple different phases of material, like from solid to liquid and
Yeah.
gas. And do you mean you can handle the combination of the different phases? Or
Yes.
like,
Yes, I can, yes, the foundation model can really handle this systems. Like for any temperatures, for any pressure, that the foundation model can handle this.
But your local descriptor, which could be, say, if you're combining the gas system and a solid system, and the average distance, say, for the atom, the gas could be really large. Do you,
Yes, but the data set contains some configurations that the distance are very large.
yeah, but do you mean actually the input of your model also, say, your local descriptor is large enough to cover, say, the range of the gas? Because
Because the, for example, I think this is the main advantage of the maze model. For example, here the figures here. As you can see, you can simply increase the layers number, and then this atom will receive the information from far away, from the atoms far away, right?
I see, thanks.
So any other questions? I should, maybe to close, we have this Math Institute here, the IMA, that actually, I think this is a residual of the IMA, this data science seminar, right? And so, long time ago, I remember we had Frank Stillinger. We had a program in chemistry, Frank Stillinger, famous for the Stillinger-Weber interatomic potential.
Yeah.
Like, maybe the first potential to properly treat silicon, okay?
Silicon, yes.
But those
So
are very
this is-
primitive compared to where we are now. It's just amazing.
Yes.
Yeah. There you go. Thank you again.
Yeah, thank you much.
I have a lot of, can you send me your slides or?
Sure.
Yeah, then I'll have so many questions for the next.
Sure,
day.
yes,
That's just
yeah.
beautiful. Yeah.
Thank you.
So,
Actually, I skip,
I know, yeah, too many questions, but
Yeah,
you know,
I
you're,
skipped some.
but you see, you're,